Hi YouTubers and BVP class. This is Cylinder Skadoo with Team 10. I'm Connor Harrison, this is Chris Gilbert, this is Melissa Van Cleek, and Lisa Nelson. And we are solving for velocity fields in an annulus. For our project, we decided to use two concentric cylinders. That is, in essence, one cylinder inside the other cylinder, and which is a more complex version of how systems work in most engineering problems. We've developed two problems, a simple and more complex numerical. Our simple problem is the two cylinders are infinitely long and stationary. We're going to ignore the infinitely long because we just need it to be, for the sake of the problem. And a real-world example of that would be a heat exchanger. Heat exchanger is two cylinders, one within the other, and exchanging liquid. One hot, one cold. Doesn't really matter which one, it depends on the problem. And the heat is exchanged between the two pipes. And that's how most boilers or other problems work. For the more numerically complex, we have two concentric cylinders. Only one, the inside one, is moving at an acceleration. A real-world example of that would be a pneumatic transaction tube you'd normally see at a bank, where you put a small capsule in an envelope in a small capsule, put in the pneumatic tube, and it shoots up to the receiver. We're going to change that a little. We're not going to, normally it's done with a vacuum. We're going to do we're not going to have any pressure. And as well, we're going to have the acceleration gravity instead of the change. And here is our two images. We have a cylinder within a cylinder, length infinite, and we're having the z in the negative direction for the sake of gravity in the more numeric problem. And here is a top view. We have the radius, kappa r on the inner and regular r for the outer, and we will be measuring the flow, or calculating the flow, in between. And we'll take them to Melissa.
So now that we've heard from Connor about the uses for this project, I'm going to talk to you about the math behind how we calculate that velocity field in the annulus. First, we start with some general equations. We start with continuity, which is basically conservation of mass principles. We're going to use cylindrical coordinates because that's what's convenient for measuring or calculating a cylinder. So here it is in cylindrical coordinates. We're also going to use Navier-Stokes, and the general form of that is right here. So the first step in any of these problems is to list out your assumptions so that you can simplify your equations as much as possible. So our first assumption for both of our problems is that we have steady laminar flow. That means that the flow does not change with time, so we can eliminate all derivatives of velocity with time. Our second assumption is that we have incompressible flow. This allows us to assume a constant density. Our third assumption is that we have Newtonian flow, therefore allowing us to assume a constant viscosity. Our fourth assumption is that in the theta direction, that's the direction around the cylinder, we have symmetry about the axis. This implies that our velocity in the theta direction, right here, will be 0, and that any derivatives of velocity in the theta direction will also be 0. Our last assumption is that we have fully developed flow, also known as negligible end effects. This implies that any change in z can be neglected in velocity because we're not dealing with entrance or end effects. So we're going to begin by simplifying each of the components of the Navier-Stokes equation and seeing what that gives us. So we're going to start with the radial component, r, and here it is in its all drawn out form. We're going to first simplify with continuity. Continuity tells us that the velocity in the r direction has to be 0 due to the kinematic condition. So you can see here that all the VR terms have been crossed out. We then simplify using assumption 4, which says symmetry about the axis. So all derivatives in theta have been crossed out as well. This yields the final form for the r component of Navier-Stokes, which tells us that the dynamic pressure for the r component is 0. Now we will move on to the theta component of the Navier-Stokes. And we simplify first with assumption 1, which says that there's no time dependence. So we can cross out our time derivative. We then simplify with assumption 4, saying there's symmetry in theta about the axis. So all velocities in theta and derivatives in theta have been crossed out here. This yields, once again, the dynamic pressure in the theta direction is 0. So our last and most complicated component, the z component of the Navier-Stokes equation, is right here. We're first going to simplify with continuity, which tells us that the radial velocity is 0. We then simplify with our assumption 1, which, if we recall, was that there was no time dependence in velocity, so that goes here as well. We then go to assumption 4, which is our theta direction symmetry about the axis, so all derivatives in theta are 0 as well. And we simplify lastly with assumption 5, which said no end effects, which means every derivative in z must be crossed out, and those are here. This yields a slightly more complicated equation that has all terms in r and all terms in z. Therefore, these two must be equal to a constant, as we'll see on the next slide. So here, all terms in r and all terms in z must equal constant. We've called it a. Now we will integrate this expression to get this result with constants a1 and a2 in it. We use boundary conditions, which we obtained from our diagram, to find these a1s and a2s, and we yield this result depending on differential pressure at the two ends of our system. For the numerical example, the only difference is that we now have a time dependence. Our gz term is no longer just a constant. We used a Maple code, using the Maple mathematical software, to find the solution at several different values for time. We plotted these on a diagram, and the t equals 0 plot line corresponds to the result that we would have gotten if we had plotted our analytical solution. So here we can see our numerical solution is much more complicated. We start with the same result, and we use differing boundary conditions to solve our a1s and a2s, and we get much more complicated a1s and a2s that both have time dependence in them. Here is the plot of our numerical example. As you can see, this t equals 0 curve is our stationary example. And as the inner wall begins to fall and time increases, you can see that the velocity at the wall is also increasing. This is logical. And thank you for watching. That was our BVP presentation. I hope you learned something about boundary value problems today.
Tudong.